So, we will discuss today band theory of solids. Okay. So, for metal we have used free electron theory. Or free electron gas model, and initially we considered classical theory and then found it cannot explain some all properties. So, then we have considered quantum theory, right. So, classical theory, their max Boltzmann distribution is used, how particles or electrons are distributed in different energy levels. So, there this Maxwell-Boltzmann distribution was it, that distribution is that is basically is this the factor, using this factor of function of energy, and but it is found that it is not correct distribution for free electrons, because electrons are fermion, it is different from the gas atoms. So, appropriate distribution is Fermi-Dirac distribution, right. So, that was that 1 by e to the power E minus E f by k t, okay, plus 1. So, that was the distribution, proper distribution, and using this distribution we are able to explain most of the properties of metal. But now question is then why we need another theory of solids, especially to explain this different physical properties of solids, including metal and others, insulator and semiconductor. So, with respect to that electrical property, material or solid was divided into 3 types, right, metal, semiconductor, and then insulator, right. So, for most of the properties of metal was explained using free electron theory, but that theory cannot tell why some metals are is very resistive, it is insulating, it shows insulating property, or it shows the semiconductor property. Also, probably you may be familiar with this Hall effect. If you are not familiar, that also fine, because I will teach you. So, considering free electron theory, so this only negative Hall coefficient is we get, but experimentally we get both type of Hall coefficient, positive Hall coefficient and negative Hall coefficient, both type of coefficient we get, right. So, this theory cannot explain the origin of this another type of Hall coefficient. So, only it can explain the negative Hall coefficient, not positive Hall coefficient. Okay. And there are many properties. So, this is not the universal or very accurate model which could explain everything, especially related to the electrical property, thermal property, also magnetic property, right. So, one thing is clear that in case of semiconductor insulator, here definitely this number of free electrons will be very small in compared to this metal, right. In metal is this huge number of free electrons are available, whereas in these two cases we hardly find the free electrons. Okay. So, it is so this theory, it is obvious that this theory is not suitable for studying the say electrical property of semiconductor and insulator. So, we need basically modification of these free electron gas model. As I mentioned earlier, this model, any model is basically it based on some assumption, based on some postulates, okay. And then based on that assumption we develop the theory, and if that theory can explain the experimental result, then we tell okay, this our assumption is correct. So, but if it cannot explain, then this problem with our assumptions are not realistic. So, one has to think and modify the assumption, take more realistic assumptions. Okay. So, that is the way this model is improved. So, here also we have seen this first classical model theory was taken, but it could not explain many things, partly it was explained. So, then quantum theory, then it is most of the things was explained. Okay. So, thus this model was improved. Okay. Then now there are some things which cannot explain this free electron gas model. So, now again we have to rethink about our assumption and find out the appropriate assumption or realistic assumption, and then we can improve this model. Okay. So, that is the next step, we are going to do this improve of this free electron gas model, and that basically that improved version is called the band theory of solids. That is the band theory of solids. Okay. So, if we revisit our assumption of free electron gas model, so in this case purely just we have considered the free electron in a crystal. Okay. So, we considered it is in a box, only electrons are there, nothing is there, no potential energy or constant potential energy one can consider, and then based on that assumption we have developed this theory. But one thing we have ignored, that it is not a just 3-dimensional box, it is a crystal, it has lattice. So, at each lattice points atoms are there. So, that free electrons are coming basically from those atoms, but ions are there, right, ions are there. So, for each electron there is a ion, and they are periodically sitting in the crystal, they are periodically sitting in the crystal. Okay. So, we have ignored the presence of these ions in the crystal, and now that was the one that major drawbacks, that was not the realistic assumption. So, we have to correct this assumption, take more realistic assumption. So, now in this case, if we consider that there are ions, they are periodically arranged in the crystal, and electrons, free electrons, it is free electrons, when they are moving, they are passing through this space between among the ions, whatever space is available through this, it is moving, right. So, ions have the potential, right. So, ions in the lattice points, so they will give potential to the system. So, now which type of potential and how we will consider the potential, whether it is constant potential or this potential varies with the distance. So, that one has to consider. So, definitely there is a potential. Okay. So, here we have considered, we have ignored the potential faced by this electron when it is passing through these ions. Another also we have ignored that, so when these electrons are passing through, these other electrons are there. So, the interaction with those electrons, that also we have ignored. So, in this model, band theory of solids, in this model, now we will consider the potential energy of the crystal system, or potential energy in crystal, which will see the electron when, that is free electron, when it will pass through that crystal. So, that potential energy we have to consider, and this potential energy, if it is say Vx, so this Vx equal to, whether it is independent of x, then it is constant, or it depends, it varies with x. So, how it varies, that we have to consider. Okay. And so why we should consider the potential and which type of potential we should consider. So, just I can tell you that, you remember when I have discussed that when atoms sit in the ordered position in a crystal, or one atom, another atom will be being close to that atom. So, there are some electrostatic force, attractive and repulsive force, and then we get a balanced position, and that is the equilibrium position. Thus, the atoms sit in the crystal, right. It forms the ordered structure of the crystal, and in that case you remember. So, when I am bringing this one atom, okay. So, one atom when I am bringing, so that potential energy, it changes like this, that we have seen earlier, right. So, similarly, if you bring another atom, so its potential energy with respect to these two, its potential energy will vary like this. So, similarly, in crystal there are many atoms arranged in a row. So, each one will face potential, and this. So, where these atoms are sitting in the crystal? So, where the potential energy is minimum. So, this is say V x. Now, this is the I am changing x. So, this potential energy at this site, potential energy at this site, okay, are minimum. Okay. So, if I consider the lattice, okay, if I consider the lattice, so generally I can, so that is lattice rho. So, let us take one dimensional lattice, right, and then I can consider that in that lattice. So, potential. So, here is if I take this is 0 level, this is 0 level. Okay. So, potential I can consider, okay, at like this. Okay. So, with respect to the negative, so here potential is lowest. So, potential is lowest. So, here the lowest potential, right. So, here you can see this, there is a, it is basically varying periodically, potential is varying periodically. Okay. This is the minimum potential, right, then it is moving this maximum potential, then it is again minimum, then. So, if this the lattice distance A, so potential is periodically varying. Here whatever potential after A distance, it is coming to the same potential. So, if V x plus A whatever the potential, so it will be equal to the V A, okay, that's condition will be satisfied for this potential in the lattice. So, here we have considered one dimensional lattice. So, there this potential is periodic. Okay. So, I told that in case of free electron gas, potential energy was considered constant or 0. Okay. That is not correct. Actually, ions are there and their potential varies like this, as we have studied earlier. Okay. And one should consider this potential which periodically varies, and it is function of x, right. So, that, so in this model band theory, this potential will be considered V x, and that potential is such that it will vary V x plus A equal to V A, right. So, it is periodic potential, and so this now what will be the form of this potential? What will be the form of that potential? That is realistic potential, but problem is mathematically it will be very difficult to handle such potential. So, we have to simplify it, okay. So one can consider this potential is a potential is like this, but still it is difficult. So, it has 0 potential for some part, and but this and this say some value V 0, okay. But problem is again it is varying like this. So, it is difficult to handle. So, if we consider this kind of square potential, so average out okay. So, it is approximation of this potential to the square potential, okay. Then we can define this potential, this if I take so it is V 0, okay, basically minus V 0, it is negative potential, but if we draw this potential just this way. So, this level we will take as a 0. If I take this level as a 0, okay, just we are shifting this one, this origin. So, that means here 0 potential, here 0 potential, here 0 potential, then this will be the, it was minus V 0, now this will be the V 0, right. I can shift the origin, So, then I can say that okay. So, now it is my 0 level, So, let us consider so now you can see as if these our ions at 0 potential, ions are at 0 potential, and so at the ion it is 0 potential, and then between these two ions, in between, so there is a potential barrier of height V 0, if I take this is the axis, this is Vx, and this value is V 0, right, this value is V 0, and this 0, this is 0, origin I am taking, this is 0, okay. This is x varying x, fine. Now, you see if I take this, okay, this it is A, it is minus B, then this will be A plus B, this will be, this is B, this is A minus A plus B, Okay. So, these are the okay. So, our potential is in this case, in our case here you see periodicity is this, right. So, periodicity is basically periodicity you can see A plus B, okay, or this you can see A plus B. Okay. So, A plus B, so this is that is periodicity. So, this Vx its periodicity will be, oh sorry, here I wrote A is not correct, it should be x, Vx plus A equal to Vx. Okay. So, then in this case, in our case, the way we have defined, so periodicity is A plus V, okay, Vx plus A plus V will be Vx, okay, for our system. And this V0 so another two condition, Vx will be 0 when x is greater than 0, and less than A, greater than 0 and less than A, right. So, then Vx is 0 and Vx is V0 when x is less than 0 and greater than minus b, when x is less than 0 and greater than minus b. Okay. So, this is the potential for one dimensional lattice, one dimensional solid, okay. And under this potential, when electron move through this crystal, so that will be the, that it will face this potential, okay. So, this periodic potential. So, here the square potential we have considered, we have assumed the square potential that was assumed by, that was square potential well, it was considered by chronic Penny. So, that is why it is called conic Penny model. Okay. And now, for free electron, we have seen this psi k, that is we have taken this psi k r, you remember we have taken e to the power I k dot r, right, k dot r. So, that was the wave function was taken. One, as I told, one has to assume wave function, proper wave function, and then we have to make this wave function for our system considering the boundary condition and other things. Okay. So, but first one has to assume a form of wave function looking at the present problem. Okay. So, for free electron theory, we have seen this type of wave function was used, this plane wave. Okay. Now, here as I told this that we have free electron, that whatever assumption that everything is there, now we are introducing this periodic potential. So, this wave function also it will be close to the this wave function for electron free gas. Okay. So, that was the wave function for electron free gas. So, in this case, so in our one dimensional case, so one can write I k x s x, right, I k x x. Okay. So, now this was valid for constant potential or the 0 potential. Now, we have periodic potential. Now, we have to consider proper wave function. So, now which type of wave function will be appropriate. So, that Bloch found that for any periodic potential the wave function this wave function will be modulated with another function, will modulated with another function, say u x, will modulate it with another function u x, okay, where u x will follow this function will follow the periodicity, of this potential. Okay. What does it mean? So, u x will be equal to u x plus a or whatever periodicity. In our case, this periodicity a plus b. So, a plus b. Okay. So, that is called Bloch theorem. That is called Bloch theorem. Okay. So, now things are ready. What I need? I need to define the potential that I have defined, and we need we have to assume a proper we have to choose a proper wave function. Okay. So, that also from Bloch theorem we are getting. So, this for we have periodic potential. So, wave function will be of this kind. Okay. So, which this u x is the u x is called the Bloch function. This u x is called Bloch function. Okay. So, I think more or less everything is fine. Now, we have formulated the problem properly. Now, we have to solve the Schrodinger equation to get the information about the system. So, I will stop here. I will continue in next class. Thank you for your kind attention.